Hello everyone, we are the team behind the multi-hybrid boost converter, also known as the MHBC. So to get into the basics of what the MHBC is and what it can offer, we should look at what is currently being used. So currently there is a PV array being fed into a DC-DC converter. This could be many different types of converters, but for simplicity's sake, let us pretend that this DC-DC converter is a boost converter that would be increasing the voltage through the system. The output of the boost converter would be feeding into a DC bus that would supply appliances such as a PV charging station or a battery, and it will also be fed into a DC to AC inverter. The DC to AC inverter converts the unused, unneeded DC voltage into AC that will be fed into the grid. Where the MHBC plays into this is that it will improve on the stages of the DC-DC converter and the DC to AC inverter. What the MHBC does is that it is fed a DC input, much like the DC-DC converters that are being used in today's design, but is able to perform a DC boost and a DC to AC conversion. The benefits of this is that it would have less power switching loss and a centralized control since only one converter is needed compared to there being two converters.
Here we have the circuit topology of our multiport hybrid boost converter. The topology is the same as a three-phase, two-leg DC-AC inverter in a grid-forming connection. Grid forming just means that the source is connected to an AC load, whereas grid following would be a source connected to the grid. The DC output is grabbed from the voltage across the resistor, while the three-phase AC output is grabbed from the node that connects each pair of IGBT switches. Normally, this inverter switches would operate on a traditional three-phase inverter PWM, but our system would not work for our hybrid applications in this case. Here is the MATLAB model and logic of our modified PWM for the MHBC. The modified PWM is fed 5 input signals, 3 of them being the AC sinusoidal waves and 2 duty ratio signals, where one is the sign difference of the other. These signals are compared to the carrier frequency and each other in order to generate the gate switching signals for the MHBC. The modified PWM is the heart of the MHBC, and without it, the system would not be able to DC boost and convert to AC in a single system.
In order to bring the MHBC in the real world, we would need to be able to generate the signals for the modified PWM. To do this, we use LabVIEW. LabVIEW is a program similar to MATLAB Simulink, but allows us to be able to export the signals from the computer via a GPIC, which we'll be going further into later. Being shown is the modified PWM in LabVIEW, and we created this display for testing. Many of these displays are there in order to ensure the safety of the tools we will be using for this experiment, but focusing on the middle right of the screen, you can see the controls of the modified PWM. With this setup, we're able to control the DST and the frequency. Of course, we're able to change both of these at the same time, and they would have no effect on each other. As you can see in the bottom left, there is a signal frequency being generated. These signals are not a perfect representation to the actual signals being used, but gives the users a visual on what is being fed into the AC side of the PWM.
So now we are looking at the compact Rio GPIC board we will be using for our project demo setup. GPIC stands for General Purpose Inverter Controller, and it is typically used for low power system testing. It can also be used for general testing of converter operations and signal generation. For our project, we are using the GPIC for PWM signal generation. We are exporting the gate signals to this board, which is being fed to the gate pins of the IGBTs. There is a resistor that feeds the gate signal to the IGBTs in order to filter some digital noise generated from the analog signals of the GPIC. So here's the lab view setup, oscilloscope and DC supply. Here's our whole setup for the demo. We'll take a closer look at the gate signals on the GPIC board. These are being fed into the blue resistors shown here, which are the gate signals of the IGBTs. Here on the bottom is our 3 legs of the AC load with our passive components, RL and C. Here's another look at the GPIC board.
And next we'll get into the hardware demonstration of it. So we input a 10 voltage and we get out roughly about 8-9 volts. That's due to the inductors having a high resistance to them. When we activate the PWM, the current shots up, and we get a boost when we have a duty cycle of 0.5 of double, which is shown is roughly 16 volts, 17 volts. And we're gonna implement a frequency to it after we turn down the duty cycle. When we have the full frequency at 60 hertz, we get 6 oscillations in the 10 milliseconds division. And then we're gonna turn off the frequency and then boost it again to 0.5 and turn on the frequency. As you can see, we are getting the boosting from the DC boost and the frequency oscillation. We are able to freely change both of these, and both of them will be changing accurately on how they should be.